Hello and welcome to today's webinar presented by Delubal Software. Today we're working in our structural analysis and design software, RFEM. The topic for today's presentation is AISI S100, CSA S136, cold form steel design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Cho will be your moderators, answering any questions you may have. They are both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So regarding the content over the next hour today, we will begin in our standalone program R section that will allow us to calculate the cross-section properties for a custom cold form seal section that will soon integrate into RFEM 6. Then we'll move on to our example as we see over here on the right-hand side with a racking structure to review the modeling and loading. We'll talk about a few specific requirements within the AISI, including the direct analysis method for stability design, as well as the direct strength method and finite strip method advantages. And finally, we'll be running the full analysis in RFEM, but also the design according to the AISI for these cold form steel members, utilizing the steel design add-on within RFEM. So we'll go ahead and get started in our standalone program R section today. So as mentioned, this program will allow us to calculate the cross-section properties for any user-defined section. We'll begin by importing in a DXF file. So I'll go ahead and navigate to the Save DXF file on my computer. And within the DXF file, I only have drawn the center lines of my custom cross-section. Because I did not draw the outer boundary lines, but rather the center lines directly, we can take advantage of this option here where we can set the thickness immediately utilizing those center lines for our custom cross-section. So we'll go ahead and set the thickness to 0.25 inches. We can also set the material within this dialog box when importing. We can visit our material library, and over on the left, we have the filters to utilize the steel dropdown and then the AISI S100. So here are all of the available materials for cold form steel. And notice that as we click through these different options, there are several subcategories as well. For this particular cross-section, we'll go ahead and utilize the A1003-15 and the subcategory here of ST33H. So that material will then be set within this dropdown, and we can go ahead and click OK. So once the import is done, we actually see everything automatically generated for this custom cross-section. Now, I did want to point out that notice that these are completely straight elements. We get a little bit better performance with the finite strip method with cold form steel sections when we just model directly these straight elements. It is possible to also model arcs at these corners where the elements join, but just know that the calculation time will be increased because of that. So ideally, it would be best to keep these as straight segments. Now, looking at the custom cross-section here, we have a couple of elements that, again, were automatically generated. We'll start off with what we call the part. And the part is automatically created between the exterior boundary lines here of the cross-section. Then on top of that, we have what we call the elements, and each one of these segments here is comprised of an element. We can right click to edit the element, and what you'll see here is that each of these has a particular thickness assigned to it as well as a length. And this information is important for the thin wall analysis and is required. So we would need both the parts and the elements. So going back to the navigator here, I'm going to right click on the model name to access the base data. There are two analysis methods. The finite element analysis is set here by default, but this would be more so used for massive cross sections. Instead, we want to modify this to a thin-walled analysis. Additionally, under the manufacturing type, we can set this to cold form. This will just be helpful once we bring this cross-section into RFEM that this data will already be set. When we click OK, we can simply go to calculate, calculate all, and immediately we'll see here that the cross-section properties are presented to us in table format. So we have the area, for example, the moment of inertia, the section modulus, and this is the information that needs to be transferred to RFEM in order to understand the cross-section properties here of this section. Additionally, you'll notice the unit stresses are given here based on a 1 kip applied load, for example, for axial forces or maybe a bending moment. We can also view those stresses with the 1 kip per foot applied to this cross-section. So once we have the cross-section properties, we do want to save this to our computer. So in order to integrate in RFEM, we do have to have these saved cross-section properties from the calculation as well. And we will jump over to RFEM. So beginning our cold form steel structure today, when we create a new model, we would give it a model name. The type of model would be set to 3D. And under this second tab, this is where we have our optional add-ons. So RFEM is the base program, and it's responsible for the modeling, the loading. We can integrate with BIM software, and it can run the full static analysis. So this means deformations, internal forces, support reactions. But if we want to take this a step further to actually carry out the design according to the AISI or the CSA S136, then we need to activate here the steel design add-on. Now under this third tab, this is where we set our standards. So we can see that we will generate our load combinations automatically according to the AISI S100. We also have here the NBC. We have implemented the latest standard according to the 2022 for those load combinations. Then because the steel design add-on is active, we see here the AISI 360 is set for hot rolled steel, and we have the AISI set for cold form. Now, alternatively, if we were doing design in Canada, we could set this to the CSA S100, and we'll see the cold form update here to the CSA S136. So once this information is input, you can see here that for the sake of time, I have went ahead and modeled our entire structure here. So this is some type of racking system maybe used for automatic storage and retrieval. Now we do have other webinars, tutorials that are dedicated to new users in the program where you can learn how to draw a beam, how to apply supports. So for the sake of time, again, we'll go ahead and just do a quick model review. So over on the left in the navigator, we have here our various cross sections. So if I edit these cross sections so we can take a closer look, we'll see here the cold form steel sections applied to this particular model. So we have some channel sections, additional channel sections with stiffeners, and that custom cross section here was also brought in from our section. When we look at our library database for our cross sections, if you want to choose a standardized section directly from the AISI, for example, if we take a look here at our channels, we'll utilize the filters once again on the left to filter to the United States, as well as the AISI D170, and we see the various channel cross sections, including hat cross sections, available to us here, again, directly from the AISI standard. Now, alternatively, if you have a parametric section that fits within the criteria listed here under thin-walled, you could simply input in the dimensions and the custom cross-section properties will be automatically calculated in RFEM directly. And then alternatively, we have the import here from our section, and that's what we utilized for the shape here in the background. I just navigated once I clicked this option to that saved file from our section on my computer, and we can bring this in like we would any other member. So in addition to these cross sections, I have also assigned a material. So similar to our section, we can always visit the material database. Over on the left, we filter to steel, to the AISI, and once again, we have access to all of these various materials directly from the standard. So now that we have the cross sections and the materials covered here, we'll also see them within our navigator over on the left. When we take a look at that custom cross-section here for our column, and I'll zoom in, and you'll notice that the program has actually rendered this true cross-section for me. And I'll go ahead and create a user-defined visibility here so we can see this in a bit more detail. So you'll also notice that for these columns, utilizing the custom cross-section, they were actually modeled in segments here. So each one of these is a separate segment. Now, there is possibility in the program to model this as one continuous column and just to keep this as one member and applying intermediate nodes along the length. But alternatively, if we do model this in separate segments, it's entirely possible to create what we call a member set. So we do this by selecting multiple segments. We can right click, and under the members option, we have here what's called create member set. So that's what you'll notice here over in my navigator, that the program has grouped together these columns. And this will come into play a little bit later on with topics like notional loads, but also the design. Again, wanting to design this as one continuous member rather than those multiple segments. You'll also see graphically the member hinges applied with the symbols shown at the member ends. So if we take a look at the types for members, we see here our various member hinges, and the member fixity all depends on how these cross sections or these members are connected to one another. So with cold form steel, it's quite typical to connect them with screws. And I have several different definitions here, just depending on what that connection is. So we have our 6 degrees of freedom. These are all based on the local axes of the member itself. You'll notice that for some of these, I've applied a spring constant. So something that's not fully fixed, not fully released, but somewhere in between. So within this model, we can take a look at the different hinges applied. They're probably a little difficult for you guys to see, but as I click through these, they are highlighted in the model depending on which member they are applied to. And finally, we have our nodal supports down here at the bottom, which were applied just utilizing the tool up here in our toolbar. And these are also a bit special in the sense that initially they just look like standard pin connections, which you'll see under this definition type that we again have 6 degrees of freedom, but these are based on the global axes here, shown here in the background. So I've restrained the translation for this pin support, including the rotation about the global z-axis, but I've also applied a rotational nonlinearity. So this is within the rotation about the global x-axis, and under the nonlinearity options, I've applied a stiffness diagram. And we now get a new tab here where we can define this information. So you'll notice that I've set this so that the rotational stiffness is dependent on the contact pressure or the downward force for these nodal supports. So as the contact force increases here, we'll see a greater spring constant, and then an uplift, we'll see that support fully fail for rotation about the global x-axis. So entirely possible here to consider more complex scenarios for our nodal supports as well. So now that we have a basic understanding of the various members within the model as well as our supports, let us move on to loading. So I have here 3 simple load cases that we can access into our load cases and combinations dialog box. So we have the first load case, which is dead load, and you'll notice that self-weight is active here, and the action category is also set, which is just dependent on the AISI S100, because remember back in the base data, this is the standard we're using to generate our load combinations. We can revisit that information here under our base tab, where we'll see the availability to change that standard if we'd like. The second load case is a live load. So action category set to live, self-weight is turned off here. And finally, another simple load case, live load 2 with the action category set to live. So once these load cases are set up, we would need to actually apply the loads to the structure. So we'll begin here with the display of our dead load. So you'll see that I actually didn't apply any additional loads to this load case. We're only accounting for self-weight automatically under the hood for that particular load case. Now looking at our live load 1, we see here, and I'll turn this into wireframe view, that we have the member load applied here at our beams, which are spanning between the columns. And a member load can be applied up here in the toolbar. But there is something a bit special about this particular member load. If I double click on it here, we'll see that it's just a standard downward uniform load of -0.5 kips per foot, but we have the ability to consider an eccentricity on the loading. So when I turn this checkbox on, I get the additional tab up here at the top. Now the default behavior for a load is typically applied at the center of gravity or possibly the shear center. But alternatively, we can move that load application up here to the top center point so that perhaps we want to account for some additional torsion within the member for the design, or we can do so directly within the force eccentricity. So in addition to this first live load, we also have this second live load, and this is also a very simple application with a single nodal load applied up here to our center beam. So this load is just essentially introducing those horizontal forces to the entire racking structure. That nodal load can also be applied up here in our toolbar. So going back to our load cases and combinations, now that we've generated those load cases, let's take a look at the design situations. So the program has automatically created 2 design situations for us, our LRFD design situation and ASD design situation. Again, these come directly from the AISI S100, and it's nothing more than just grouping together our factored load combinations for the first design situation and our unfactored load combinations for the second design situation. We can always click on this little info button here, which will pull that information directly from the standard of what we're referencing. Design situations are absolutely needed when it comes to carrying out the design within the steel design add-on that we activated. So that's why you'll notice that these are by default checked on here for that particular add-on. Now, if we go to the load combinations, we see here those individual load combinations listed out based only on the load cases I've created under that second tab here. And we see the factored load combinations in orange belonging to the first design situation and our unfactored load combinations belonging to that second design situation. So while we're within this topic and within this dialog box, I do want to discuss a few of the requirements for the direct analysis method in the AISI standard, which is given in section C1. So a lot of these requirements do align almost identically with the AISI 360. And to begin, a second order analysis, which considers both big P delta and little P delta effects, are required according to section C1.1. Well, you'll notice that for these design situations, we have here a combination wizard settings. So if I go into edit the existing definition type here, you'll see the static analysis setting dropdown is automatically turned on to second order analysis. This second order will account for both big P delta and little P delta effects with doing nothing further to the members. I don't need to add additional nodes. All of that is considered automatically. So therefore, we can go ahead and leave these static analysis settings set to second order to fulfill that requirement. The next topic is a consideration of initial imperfections set forth in chapter C1.112, and we have the ability to directly model the imperfections, but alternatively, the easier approach is probably just to apply notional loads. And these notional loads are usually applied to the members that are taking most of the gravity load, so we might think of our columns here, and it's applied to the top of the column to create the greatest destabilizing effect. So if we look back here at our model and keep in mind under this second live load, particular load case here, we have this horizontal load. So therefore the notional load to create the greatest destabilizing effect should probably likely be in this same direction. So those notional loads all just depend on the load magnitude and direction here for our load cases to consider that destabilizing consideration. So we want to begin by creating these notional loads with what we call imperfections. So I'll begin by creating a user-defined view here for only my member sets. So we'll go up here to our toolbar and create that user-defined view. I'll go ahead and turn off the hidden objects in the background. Now, additionally, when we create our imperfections or our notional loads, these do depend on the local axis system. So if I right click, I can turn on the local axis system of all of these columns. So we'll take a look at the elevation view here. Now, the imperfections are going to be available under our navigator here under the imperfections table. So we right click to create a new imperfection case. Now, again, the imperfection directions or the case all depends on which direction you want to apply them in your model. For our case today, I'm going to create two simple imperfection cases, one in the global positive X direction and one in the global positive Y direction or into the page here. Therefore, I need two imperfection cases. So we'll begin with imperfection in the X, and then I simply make a copy of this and I'll create my second case imperfection in the Y. Now, the imperfection type within this dropdown will be set to local imperfection. And under the assignment tab, there is the ability to assign specific imperfections or notional loads to specific load cases. Alternatively, though, we can just apply it to all of our load combinations, which is what we'll be doing today. So now that these imperfection cases are generated, we need to actually apply the notional loads to the structure. So now you'll see here under our imperfections folder, these two imperfection cases. Now we can apply according to each individual member, or we have the ability to apply to a member set. And because these columns are individual segments and I created member sets to group them together as one continuous member, then we will want to right click here to create a new member set imperfection. So within this dialog box, we use our drop down to directly select the AISI S100. And this is going to reference equation C1.112-1 directly from the code. So this should look familiar if we look that up within the code. So more or less, we are just applying a deflection here at the top of our columns, but the deflection magnitude all depends on the axial force applied to the member. So this is an iterative calculation that the program will go ahead and automatically apply for us based on the axial forces under each load combination. The imperfection is applied according to the member's local axes. So for our case today, this first imperfection in the X direction, we want to apply this based on the negative Y axes. And I'm going to select here my member sets in the first row and the third row. And we might be wondering, why are the local axes different here for the different member sets? And that's because in row 1 and 3, I have the members rotated at 90 degrees. And then at rows 2 and 4, they're rotated at negative 90 degrees. So inevitably, this affects our local axes orientation, which is why we need to take a two-step approach here for the imperfection direction. So now that I've applied it to those particular member sets, I can click Apply and Next to remain within this dialog box and to just simply modify my imperfection direction to the positive Y local axes. I'll go ahead and select these graphically as rows 2 and rows 4. I click OK. And I click OK once again. Now, if we display our notional loads here, or imperfections, we see that column out of plumbness here applied, again, referencing the AISI to our member sets or our columns directly. We're going to do the exact same approach here for our members for imperfections in the Y direction. So we go back to our navigator to right click to create a new member set imperfection, this time under the imperfection Y case. We'll select the definition type directly as the AISI S100 once again. The imperfection direction this time is going to be in the negative Z axis, and I will go ahead and zoom in here to select the member sets in the first row and the third row. I click OK, apply and next, and then we just simply modify this to the positive local Z axis to select our member sets in rows 2 and rows 4. I click OK through these dialog boxes, and now we should see this column out of plumbness, and I'll go ahead and right click here to turn off the local axis system applied in the global Y direction. So this is how we can directly account for those imperfections based on the code requirements. Now that we have applied the imperfections in these various cases, we need to combine into the actual load combinations. So I'll drop down here to my dead load, and this will allow me to access the load cases and combinations dialog box. And under the design situation where we had previously set the second order analysis, we'll go back into this dialog box, and you'll notice here that we have a checkbox to consider the imperfection cases that is automatically turned on by default. So therefore, for my factored load combinations, those imperfections will automatically be added in to the existing load cases as well. Now, the problem is that I want to carry out LRFD design for today for my cold form steel structure, but I'm using my ASD design situation for maybe my serviceability or deflection checks. Therefore, I don't want to consider my imperfections for this second design situation. Well, it's easy enough to create a copy of this existing definition type, and within this copy, I just simply turn off the imperfection cases. So now going back into my main dialog box for my factored load combinations, we'll keep this as definition number 1. But for my unfactored load combinations, we're going to drop down and select the third option here where we turned off the imperfections. So now when we jump to the load combinations, we see here our factored load combinations, and you'll actually see a duplicate copy here for every factored load combination. And this is because we have imperfection in the X applied and imperfection in the Y. Same concept for the next load combination, imperfection in the X, imperfection in the Y. But for my unfactored load combinations, you'll see here those imperfections are turned off. The final topic, according to the direct analysis method, is stiffness reduction, and this is given in section C1.113. We reduce this stiffness to account for inelasticity effects as well as cross-section deformations. So in order to take into consideration the stiffness reduction, we are once again going to go in here to our combination wizard settings. And this option is actually controlled directly here with a new structure modification. So we create a new definition type, and we're going to be applying this to our members. When we turn this on, we get an additional tab here, where under the member modification, we can use our dropdown to create a new member stiffness modification. Now, very similar to what we saw with our imperfections or our notional loads, we also have the AISI S100 available in this dropdown. So this will reference the code directly and the particular equations given here to iteratively calculate this tau sub B factor that will be applied to the flexural stiffness for each member. And again, this is very similar to what we see within the AISC. Now we also have an additional factor here of 0.9 that's applied to both the flexural and the axial stiffness. Now difference here from the AISC is that within the AISI, this is 0.9, but within the hot rolled steel standard, this is 0.8. So that is one difference that you'll see here. Now, the code says to apply this stiffness reduction, once we have defined this, to all members that contribute to the lateral stability. So we certainly could use this option here to graphically select those members, or we could input in the member numbers. Now, alternatively, we can just apply the stiffness reduction to all members. The code goes on to tell us that this is also possible. So if we use our drop-down box for all, we'll now apply those stiffness reductions to all cold form steel members within this model. But yet again, I only want to consider this for my strength design, which will be carried out with this LRFD design situation. For my unfactored load combinations, I do not want to reduce the stiffness, so I simply leave this unchecked here. So once again, we'll go back to the load combinations to check this out in more detail. And sure enough, for each factored load combination, we see the additional setting here to reduce the stiffness. But if we jump down to our unfactored load combinations, this option is turned off. Okay, so now that we have fulfilled the direct analysis method requirements, we're technically ready to run the full analysis. But the huge benefit of RFEM 6 is this better integration of these add-ons for the design within the main program. So we'll go ahead and continue on with some of the design input information specific to the AISI to carry out that workflow. For this, I'm going to go back to the PowerPoint here because I do want to talk in a bit more detail about the member buckling behavior. Very important topic when we're talking about these very thin-walled cross sections. So we know that there are failure buckling modes that are typically caused by compressive stresses on our members. And this is usually seen when we have a bending moment or an axial force. Well, when we're talking about cold form steel, there are 3 buckling modes that we typically consider. The first is going to be local buckling. So this is essentially where the elements bend with no translation at fold lines. And what I mean by elements, if you remember back to our custom cross section here, each one of these segments is a particular element. Well, what we see also with this failure mode is that we have a short half wavelength. And what I mean by wavelength is this is the length at which the buckling shape repeats along the full member length. Now, additionally, we also have global buckling to consider, and this is lateral bending of the entire member, and we typically think of this with flexural torsional, or lateral torsional buckling. Now for this, we'll see one long half wavelength, which is always dependent on the unbraced lengths for these particular buckling modes. And finally, a bit more unique to cold form steel is distortional buckling. So this is more or less a combination of local and global failures, where we have some translation at the fold lines, but also the half wavelength is somewhere between what we see for local versus global. Now, there are 2 methods throughout the AISI to address buckling. The first is the effective width method, and the second is the direct strength method. So going to our next slide here, let us talk a little bit more about the effective width method versus the direct strength method, and maybe some advantages here that we have. So the effective width method essentially will consider each individual element here. So again, these elements are what comprises up our cross section. And an effective section calculation is required for each one of these elements. And we really don't have any interaction between these elements for the overall member or section behavior. Now, alternatively, when we turn to the direct strength method, and this is going to be the method that RFEM is going to utilize, this has definitely some advantages in the fact that no effective width calculation is required for each one of these individual elements. There's no iterations required, but rather the gross cross-sectional properties are used for the entire section. We also have the interaction of all elements for all stability limit states because we're not considering, again, these individual elements, but rather the full cross-section itself. We also have compatibility and equilibrium maintained at the element junctures. So where these elements connect is specific to the direct strength method that alternatively, the effective width method, we more or less are not accounted for. Direct strength method is also applicable to a broad range of sections. We might see more limitations when we talk about the effective width method and which cross sections it can be applied to. Direct strength method, we really do have a lot more freedom here to apply this to pretty much any custom cross section as well. So overall, we're going to see a more accurate strength prediction than the effective width method. And this leads to more economical design. If we can better predict the strength of our cross section, then more or less this is going to lead to a better overall structured design. So within the direct strength method, there are critical elastic stresses or forces that are required to carry out the buckling design. And when we refer to Appendix 2 within the AISI, the code tells us that the finite strip method is an acceptable numerical solution that we can apply. So what we do here with the finite strip method is to treat this section as a simply supported member, and we analyze the buckling behavior with plate bending strips. From this information, we're going to get unique buckling mode curves that will be generated for each cross section. So very unique to each cross section, whether it's one from the standard or a custom cross section as well. Now we consider this for the 3 different failure modes. So we have here local, which is shown here with point A. We have distortional, shown here with B, and we have the global failure shown here with point C. Well, we'll see in just a minute that within RFEM, we can actually view these 7 finite strip method signature or unique graphs directly in the program for every cross section. And what we can display here are the local distortional and global curves, as we see here in red, green, and light blue. But additionally, we will plot the total curve, which is shown here in dark blue. And this total curve combines all of these failure modes for a quick evaluation of the cross section based on the curve minima. So when we look at the first minimum on the total curve, this is going to be our capacity for local buckling. When we look at our second minimum along this total curve, this is going to be the capacity for distortional buckling. And as this curve begins to flatten out here, this is what we will reference for global buckling. Now, this is certainly a very interesting and complex topic, so I would refer you here to some knowledge-based articles that we have directly on our website that explain the finite strip method in more detail. It directly references the AISI. Those hyperlinks are included in the PowerPoint handout that you can access within the GoToWebinar to see those on our website in more detail. Okay, so what we will do now is to go back to the RFEM model, and I'm going to revisit the cross sections here. So looking at the various cross sections, and we'll immediately jump down to that custom cross section from our section in particular. If we use our drop down over on the right, here are those 7 unique graphs that I just mentioned for the finite strip method. And these are all based on the applied unit load. So if we take a look at 1 kip axial force, what we will see is that finite strip method plot, again, referencing that PowerPoint. And this currently is showing the total curve. But additionally, what we can do here is to plot the local curve by selecting it within this dropdown. And we see that appear over here on the left-hand side with the red curve. We can also display the distortional curve. And finally, we can display the global curve. And ultimately, that total curve is going to consider all 3 of these, again, for just a quick evaluation here based on the curve minima along the length. So this is what's happening underneath the hood for every single cross section, again, even if it's a custom cross section. So now that we have a better understanding of the direct strength method, finite strip method, we'll go ahead and take a look at global buckling now in a bit more detail with effective length definition. So when we design our members, we need to input information such as unbraced lengths. We'll begin here with activating only my rectangular HSS section. So let me go ahead and show the rendered view of this so you can understand exactly where these cross sections are. So these rectangular sections are spanning in between my columns. And we'll begin with the effective length definition for these particular members. So we highlight them all, we double click, and what you'll notice is that the design properties here is turned off. This is telling the program that I'm not interested in carrying out the actual design according to AISI. Rather, I only want to carry out the analysis. When we turn on the design properties, this is going to reference the Steel Design add-on, and we get additional tabs here up at the top. So this is all information that is specific only for the design. Under the design types, we have here the effective length definition. So let us go ahead and access a new effective length definition. And you'll see here I can modify my view over within this dialog box so we can see those HSS members spanning between the columns. We immediately want to change this to the effective length definition according to AISI S100 for these rectangular hollow sections. Then you'll notice that for global buckling, we have here 4 considerations: flexural buckling, strong and weak axis, torsional buckling, lateral torsional buckling. We also have the ability here to determine the elastic critical stress according to the finite strip method or according to chapter E2 F2.1. So this is a really important topic. So I'm going to jump back again to the PowerPoint here to explain in a little bit more detail. So you'll notice within this dialog box, as I just showed you, that we have 2 options here to determine the elastic critical stress. And the first option being the finite strip method or the numerical method. And this is going to be applied then for local, distortional, and global elastic buckling failures. But it should be known that if we do choose the finite strip method, that flexural and torsional stability failure modes are always grouped together for the global buckling. And this is regardless if we uncheck one of these options. So if I am thinking, okay, my member is fully restrained against torsional buckling, but I'm still concerned with flexural buckling, so I fully uncheck this option, the program doesn't care. It still sees these grouped together because we're referencing the finite strip method graph. So this is purely a limitation of how these graphs are created, that flexural and torsional buckling are always grouped together. Now, alternatively, if we leave these checked, but we have varying effective lengths or unbraced lengths for flexural versus torsional, again, because these are grouped together, we are always going to take the longest effective length. So if we would like to set a smaller length for torsional buckling versus flexural, again, the program just groups them together for those particular global stability checks and will reference the longest effective length. So just keep that in mind with the finite strip method, again, with the global buckling. Now, alternatively, we have here the analytical method according to chapter E2 and F2.1. So if we use this alternative method, keep in mind that this is only applied for global buckling. The finite strip method and those plots that I just showed you are always used for local and distortional buckling. So we're talking only about global buckling here and the particular stability failures shown right above this with flexural torsional and lateral torsional. I would highly suggest to use the analytical method then if you have varying effective lengths for flexural versus torsional, or you want to turn off torsional but still check flexural, for example, then you would go ahead and reference the analytical method instead. Okay, so now that we have a better understanding here of what these various settings are, for my particular example today, when we have something like a tube section, we're really not interested in torsional buckling or lateral torsional buckling. And because I'm unchecking this, I'm going to utilize the analytical method here, because remember, the finite strip method would not detect the torsional buckling being unchecked. The program would give you a small warning, just letting you know that, hey, we see that you unchecked one, but we really can't consider it. So we'll utilize the analytical method. Under this second tab, this is where we apply our intermediate supports, and you can see the program automatically will apply these at the member ends, and we will be fixed for flexural buckling in the strong axis as well as the weak axis. So that effective length, KL, will automatically be calculated for all of these members shown here. So once we are done with the effective length input, we also have the ability to apply a local section reduction. Just keep this in mind that this is only for the tension design according to the AISI. We do not carry out any equations at this point in time for cold form steel considering holes. So everything is considered without holes. Under the design configuration, we have here our strength configuration. So we take a look at the default settings here, just some various settings that we have put in the code references directly for alternative equations. So you could certainly take a look at here and make those modifications if you'd like. Under serviceability, this is just simply where we set our limiting deflection ratio for our deflection checks. So for simply supported members, we will reference this L/360, and for cantilevers, we'll reference L/180, but of course you can make modifications to this design ratio here. And finally, we have the design supports and deflection. If I do absolutely nothing within this dialog box, the program automatically assumes that it's supported at either end. Therefore, we're going to reference the L/360 limiting deflection ratio. For our case today, we'll go ahead and leave this as default and not make any further modifications here. So now that this information is complete for these rectangular sections, I'll go ahead and cancel out my visibility here. I also have carried out the same workflow for my member sets. So remember, I want to design these columns as one continuous member. So rather than going into the individual member settings, we can come in here to our member sets. And what you'll notice within this dialog box is that this also has a design properties checkbox. So when this is turned on, we have some additional settings up here at the top within these tabs that look identical to what we just covered. Now, because this column is certainly much more complex, I went ahead and defined the effective length already here. So you can see that I have flexural, torsional, lateral torsional buckling all considered. I'll go ahead and change around my view here so we can see exactly which members we are looking at. I am referencing the analytical method here because I have some different unbraced lengths for torsional buckling versus flexural buckling. Now we have the ability to detect these intermediate nodes along the entire length, and notice that there are 4 degrees of freedom. This just all affects the effective length definition here for flexural buckling in the strong axis, flexural buckling in the weak axis, torsional buckling, and lateral torsional buckling. So depending on our particular connection and what members are framing in here, we can set these accordingly. And alternatively, if you have absolutely no interest in inserting in all of these intermediate supports, you can check on the absolute values here and directly input KL for each of these failure modes. And the downside to this is that if the model has any changes, we make maybe nodal location, we modify these slightly. If we use these options up at the top, everything will be automatically updated for our unbraced lengths. Alternatively, if we override these, we would need to come in and to manually modify them, but that's certainly an option that you can take advantage of. Also, under the design supports and deflection, you can see here that I have assigned specific design supports depending if the member is supported in the strong or weak axis direction. And these are applied all along the member length because I really don't want to reference the full column height for my limiting deflection ratio. But rather I want to reference the L, or the length, in between these intermediate supports. And we do so with the design supports. And notice that all of these intermediate nodes were directly detected within the program. Okay, so now that we have this information defined, such as unbraced lengths, we'll go ahead and exit out back to the program. And we want to jump down here to the steel design add-on. And you'll notice under this first tab, we have our design situation. So I had mentioned that if we carry out the design, we have to use these design situations. And the reason why is we see our first LRFD design situation that we are going to relate in the second drop down here to the strength limit state according to LRFD design. I'm using my second design situation, ASD, and I'm relating this to serviceability. Now, alternatively, if we were carrying out ASD design, then maybe we would turn off altogether LRFD. We would set our strength limit state according to ASD for our ASD design situation. We can make an additional copy of this design situation for serviceability as well, or we could create our own custom design situation for serviceability. Again, for our example today, we'll go ahead and carry out LRFD design. Under the second tab are the objects to design. Now you'll notice that defaults to designing all members and all member sets, but we have many members that are essentially given to us over here in this column in red, and that's because they don't have an effective length defined. So the program won't be able to design them, of course. So rather than designing all members, let us go ahead and graphically select here by clearing out this entry, and I'll turn on only my HSS sections so that I can graphically select these. The member numbers are automatically input here. And now we're ready to carry out the design for this simple example only for my rectangular sections, but also for all of those member sets or each of those columns. So we go to calculate all. Now, because of the finite strip method, remember for all of these individual cross sections, the calculation time does take a few minutes. So rather than waiting for that, we will jump to an already saved model here with our results. So once the calculation is done, we are currently looking at the steel design add-on, but we now have available to us the design ratios on the members. And we could view these design ratios in the table format here for each individual member. And you'll notice that as I click within this table, the program will automatically sync here in the graphical view to show me exactly which particular member I'm looking at. That red arrow is showing me for that particular check exactly what's controlling. But maybe we look at the design ratios by the cross section because I've only designed 2 cross sections for today. We have here our custom cross section from our section that we brought into the program, as well as our rectangular hollow section here. And you'll notice that we are checking every single chapter here for our strength design as well as serviceability, referencing each chapter. Now, if you're only interested in the max design ratio, we could always use our filter here to select the max. And now we see just the controlling design ratio for this particular cross section. And for these individual checks for each chapter, we can access what we call the design check details. So this is new within RFEM 6, that for all of these code calculations, you'll notice here that we list the formulas line by line. We have all references to the AISI standard, and we have all the variables also listed out here, and ultimately how we are calculating this design ratio. So trying to be as transparent with this information as possible so that you can follow along with your own hand calculations to ensure that you agree with the program's output. We can print this to our printout report. What's nice is that if we do this and we make any model changes, we rerun the design, the picture of these calculations will automatically update as well. We can jump down to any different particular check here to view the various formulas for chapter E, for example. Also within this dialog box, we can access what's called the diagram in section. So under my drop-down box, we see our custom cross-section here where we can view the stresses. And within this additional drop-down box, we can view the total normal stresses, or we can view the total shear stresses, or perhaps we're interested in the von Mises stresses. And this is all for load combination number 5 at the X location of 0. So just trying to give you a little bit more information here in terms of the stress output for these cross sections. So now that we have viewed this information in table format, notice that over on the left under the steel design, we can turn on and off the various design ratios shown graphically here. Currently, we're viewing just the overall max ratio envelope, but you'll notice under these options, we can individually select the different checks. So backing up a step, if we also use our drop down here to take a look at the static analysis. So we're currently viewing any one of these load combinations, and this was the static analysis carried out directly within RFEM. So we can view the global deformations, for example, and perhaps I change my deformation display to colored cross sections. We can also view the member internal forces. So we can view the axial forces or the shear forces, bending moments. If we zoom in here, we can right click on one of these members and access what we call the results diagram. And you can do so with individual members or groups of members. This will allow you to turn on these internal forces or deflections and view in a bit more detail what's going on along the member length. We can switch to a different load combination here. We can add this information to the printout report. We can smooth, we can average out these forces. So quite a bit of information here that we otherwise wouldn't be able to do graphically. And you can slide this over to your second monitor and work concurrently in the program. So in addition to the graphical output, we also have our table output for the static analysis, where we can view the results by members, such as the internal forces. We can export this information to Microsoft Excel with the click of a button up here for further sorting capabilities. So hopefully this just gives us a nice overview then of the full analysis and design workflow for these cold form steel sections according to the AISI. As we know, identical workflow for the CSA S136. So in the final few minutes here, I do want to turn to a topic that is maybe a little bit more unique for an FEA program. And this is web crippling design. So typically in a lot of FEA programs, we just simply can't account for these additional checks. But within RFEM, we actually have integrated these. So we can carry out the design of web crippling according to section G5, and this is web crippling without holes, as well as section H3, which is combined bending and web crippling. Now, this is only applicable for sections that are referenced directly within the standard, in particular table G5 1 through 4. And those sections are listed here. So any other cross-section outside of this list, we won't be able to check web crippling, so you would need to manually take that into consideration. Another requirement is that the member must have 0 rotation set. So we can't rotate this member 90 degrees or 180 degrees. We need to leave it at 0 if we do want to carry out these additional checks. And finally, the last requirement is that we have to apply what we call the steel design supports. And this will allow us to directly reference these tables from G5 in order to carry out the full web crippling calculations. Now, we've already talked about design supports within our example model today that we use for deflection. So what we'll do is to go back to the RFEM model in the last couple minutes, and I'll pull open this simple single beam element here. And this cold form steel section, if we zoom in here, is just a typical channel section with some stiffeners added at the end. And this was from the AISI database within RFEM. And we have a uniform load here at 0.22 kips per foot along the full member length. Well, if I double click on this section, everything is as we've already learned from our previous example, except for let's take a look at the design supports. So you'll see here that I have already defined supports at the 2 ends as well as the interior with that automatically detected node, but we do need to create the design support definitions. So you can see the first one, I have labeled this as the end support, and the type in this dropdown is set to steel. If we have this set to general, we'll only consider these design supports for deflection. But when we have it set to steel, this will allow us to further carry out not only the deflection checks, but also the web crippling. So you'll see that I do need to give it a support width. So we enter in the support width. For my end support, I set this at 3 inches. We need to tell the program if it's an end support, if it has an overhang length, and also is that support fastened to the member. And this information is all important to reference to chapter G5 from the AISI. Without it, we wouldn't know what variables such as safety factors, resistance factors, coefficients to reference without directly inputting it in here. Now I also have a second definition for my interior support. So if these supports vary, that's no problem. We just create a second definition type here. The type is set to steel. My support width was decreased to 2 inches. It's not an end support, and maybe it's not fastened to the member. So once we have the definition set, then we just simply use our drop-down box to assign them to the nodes along the length of the member. So once this is input, we can take a look at here at our steel design results. And you can see that my design ratios here, except for these ones shown in red, are very low. We have 0.304 or lower for this particular cross-section design according to the AISI. These two checks that are over the 1.0 ratio are specific to web crippling. So you can see how maybe perhaps if we forgot to carry this out, the member looks like it's passing quite well. But when we add in these additional web crippling checks, we see that actually the member is not adequate. Again, web crippling according to G5, as well as combined bending and web crippling according to H3. We can pull open the design check details here, and we can see all of the information where we will reference those tables in G5. We list them out here in table format as well, and ultimately how we're calculating that design ratio for web crippling. So just an added benefit here of RFEM, again, that many FEA programs can't consider, but because we have those specific steel design supports, we can carry out this additional check. Okay, so we will go ahead and conclude our webinar today. This webinar was recorded. It will be placed on the same webpage that you used to register. You can also download now the models that I used in the presentation. So all 3 are available, including our section and the 2 from RFEM. And you can download the free 90-day trial version. So this trial version of RFEM 6 is full capability for 90 days. It includes all add-ons, including the steel design add-on. So you could download those example models and open them up in the trial version. If you have any questions about today's presentation or any other question related to the RFEM products, feel free to contact us at our Philadelphia office shown here at the lower of the page. Our phone number is 267-702-2815, and our email is info-us@duluval.com. So we will have many more upcoming webinars. We try and hold these approximately once a month. You can register at duluval.com under support and learning webinars. As most of you know, I will send out a reminder email about a week before these take place, so you can keep an eye out for that. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So that is a requirement of the states that we are pre-approved providers in, that you are here for the full duration of the webinar in order to receive that PDH. Now, if you watched with a colleague or in a conference type setting and you yourself did not register for this GoToWebinar, you will need to request your PDH here at info-us@duluval.com. So go ahead and send us an email if, again, you yourself did not register with your own name and your own email, but you were here for the full presentation and would like PDH, go ahead and let us know who you watched it with by sending us an email to the address shown here. It should be known that it's not automated, that the PDH goes out directly when this webinar ends. It will usually be sent within the next 24 hours, so keep an eye out for that. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at the next presentation. Thank you.